All right, so we'll kind of continue on to our time series. I think I always just blend sections 31 and 32 together since they're basically just all time series the whole way through. Where I think section 31 is more like the introduction to time series, the trends and stuff like this, like introducing it. And then 32 is really focused on the modeling aspect. And so I'll kind of go over a few over the concept of like the modeling and stuff like that. Most of it, if you guys haven't gone through the labs, I think the labs give like the most part of like the modeling, like just being able to kind of perform them, but kind of like do a little bit more review if you guys have already gone through those sections. So let me go ahead and pull time series up, and I know we have a notebook we hadn't finished yet, which is all good. Okay, so I think last time we stopped, correct me if I'm wrong, about right here, right after the dickey-fueller test, right? So I'm just going to make sure in case there's anything I need to run from before that I need. I don't think I need anything else, but we'll go into removing trends. So we kind of talked about kind of quick review, right? We had our rolling statistics talking about how we can basically average over the previous values to kind of smooth things out and stuff like this. That can help like get rid of some fluctuations, especially highly like if you think like a lot of variance in like the Y direction where like it fluctuates a lot. It might be nice to kind of smooth that part out to make it a little more easy for us to understand what's going on here, basically getting rid of all that extra noise. So you'll see rolling statistics happen more frequently. Just kind of talking about some trends, right? We said basically the different types were stationary, and then we have our linear upward trend and downward trend, exponential trends are periodic. Also, you can say seasonality. So like that periodic where we're going up and down, going through. So kind of look for everything. Awesome. And let's see here. So let's go into the next part. So we talked about the different trends. Okay, so now we're talking about removing trends. So our goal basically, like I kind of hinted a little bit before, is that we really want a stationary model, right? And the reason why we want a stationary model, and oh, hey, Phyllis. See you came in. Let's see this. The reason why we want a stationary model is we want to basically explain those trends. If we can explain those trends in the model and stuff like that, basically it means that, or if we can remove those trends, it means that we understand them, essentially. We're trying to say, hey, like how does basically time affect the values? And if we can say, oh, over time it goes up by this amount, or, oh, we see like every, let's say 6 months, it kind of goes up and down, we can take that out of our series and say, oh, well, we can explain this part and can always add it back in. What we want really is that stationary part, which basically like you can think of like white noise, like essentially like randomness, because that randomness is represented, like I call it the noise, but really it's not a really accurate way of saying noise, because that stuff usually is like other factors that are in the time series that we hadn't considered. Basically things in this case outside of the time. So you can think of other factors that are affecting this series, and that's what we'd want to look into. So that's the real reason why we want to get into the stationary series. It's sometimes thought of like independence. Like if you remember, we always want like independent data that's kind of independent. Stationary is kind of saying it's independent from time. So like it's no longer dependent on the time itself. Okay, cool. Does that make sense to everyone? Why we're getting into stationary? Okay, cool. So our first kind of strategy is like, well, let's go ahead and try doing a log transformation. So we're going to take the data here. I'm just going to, here. Why did I put this out? Hopefully this runs fine. I might have changed it up. Okay, so we can see we took our data. In this case, I'm trying to look, where is our plot? Oh, our time series, there it is. So this is our time series. I think it was the exponential trend that we saw before. And we're just plotting out the different parts of seeing like, this is the original data here. And I think it's actually from the curriculum. We do a log transformation. So you can see how it kind of goes up here. And as we get if we do a log transformation, it kind of flattens this part out, which kind of makes sense. Opposite of exponential is logarithmic. You can also do things like square root transformation. So you'll notice that the square root also does very similar stuff to this, and it basically flattens out. And the reason why you might want to do like a square root transformation over a log transformation is to punish the values less. So the log transformation will punish very extreme values much more. And so you can kind of see this heteroscedasticity, right? You can see that this model, when we do the log transformation, starts off with high fluctuations, but as we kind of like go further and further, 2017, 2018, you can kind of see this cone get smaller and smaller, and that's not ideal. So you might want to try out, like, let me see square root, and you can see square root here doesn't punish those values as extremely, so you have a little less heteroscedasticity, but you also can see it's not as linear as we probably would prefer. So kind of know that, you probably won't get it perfectly. For the most part, you'll see most people end up using log transformation. It's just kind of like the gold standard for most people. But it's nice to know that there's other transformations to help flatten that part out. Okay, cool. So so far, so okay, cool. We got, like, if you imagine this either log or square root, we basically got rid of that exponential trend, right? So it's like, all right, cool. Like, let's go ahead and smooth it out by subtracting the rolling mean. So what's really nice about the rolling mean in this case too, it'll actually also flatten this part out. So in this case, we already saw how to do the transformation with a rolling window. I'm going to use a window of 4 in this case. Note in this case, I end up using the square root because I like this heteroscedasticity a little bit better. Like, it's not as heteroscedastic, so I like this, kind of this fluctuation between each time, or previous time and stuff, like a little bit better. So I use the square root in this case. And let's go ahead and just show this plot now of the rolling mean of 4. So you can see here, it gets in this red, is that we can kind of smooth this part out, and we want to kind of get rid of that extra fluctuation just to see, like, well, can we just explain just this upward part? And so if I subtract this part off, which is nice, is I'm basically just subtracting off this average going up. So I can tell it's going up higher and higher and higher. And what I can do, I can subtract this off, and this will bring it down now, essentially move, excuse me, sorry, I have a little bit, gonna sneeze or something. Okay, so you can see as we kind of like have this trend that's going upward in the rolling mean, it's also going with our actual trend after the transformation. And what that will do when we subtract it, it will actually bring it downward, right? It'll basically flatten it across. Basically, I'm just going to look at, like, how much does it fluctuate from this rolling mean? And so we should get something that's relatively flat. So if I do this now and plot this, oh, I'm dropping out these values too, since basically if I subtracted, there's nothing there. So I'm just dropping out the null values, and then I go ahead and plot this. And you can see now is that looks a lot better in the sense of, like, what we would expect for, like, kind of like something that looks stationary. You can probably see, like, maybe there's some heteroscedasticity, which kind of makes sense because we did notice that there was a little bit of heteroscedasticity in the square root transformation. But this might be reasonable in the sense of expecting this to be stationary. A couple of things to note is that we subtracted the rolling mean, but sometimes you can actually do a weighted rolling mean. So I don't actually implement this, but it's an important part to ask, kind of recognize. And the reason why you might have a weighted rolling mean is that the rolling mean here, when we basically have, like, our rolling statistics, when we're taking the average over the 4 previous points, we're basically saying 4 days ago, 1 day, 3 days ago, 2 days ago, 1 day ago are equally weighted into predicting the next point forward. And you can probably think about that, like, that's not probably true. Like, it's probably more important to think of the most just yesterday versus 3 days ago. Like, this should have more weight in deciding on what the next factor is. So that's where you would have something like a weighted mean, where you say, hey, let's go ahead and weight the most previous day, the most weight, and then kind of like the weights kind of drop off gradually, mostly exponential. So you can imagine, instead of just dropping off, like, by steps, it's kind of like this kind of smooth curve where it decays, where technically a year ago does matter, but it matters a lot less than it does for like just yesterday or a week ago or whatnot. So that's the idea of this exponential weighted mean. Okay, cool. All right. So once we have this guy right here, so we have our thing, we're like, all right, cool. Like, it looks pretty stationary, but, like, we can go a little bit further. So one thing we can do is differencing. So our differencing basically is trying to get more of that kind of, like, extra fluctuation out. Can we explain it basically from the previous day? So this is also called, like, lagging. And basically the idea here is when we do a difference, we're saying, can you explain the point just by essentially looking at the previous day? And if we can do that, then basically there is some time dependence in that point. So that's where this differencing comes in. So you can kind of look a little bit on the documentation here with the data frame and the difference. Basically that will allow you to lag it over. So actually, maybe I'll show you guys real quickly what this looks like. So you can see here, these are different values. And essentially when you do a difference, essentially it moves one of those columns downward and subtracts it from itself. So that allows you to basically to see what the difference is from the previous day. So just some quick examples. We have our New York Stock Exchange with just the time series, so no transformation, whatever. We're looking at just 1 day previously with the difference, and we can see what this looks like. And you can see that this actually makes it pretty stationary pretty quickly. Kind of fun fact is that differencing, also sometimes called like the naive modeling, naive models, is basically just saying, hey, can you explain the previous, like, can you explain the value just by looking at the previous day? And this typically does a pretty good job because there is a time series dependence. You don't really like usually this will do a pretty good job compared to like you see like all this transformation we just did. Usually our differencing will kind of like immediately do a pretty good job getting to a stationary model. So note that that tends to be like one of the first steps of seeing, hey, can we just do that? And then trying to see if we can do better than this differencing. Similar with the temperature data. So our temperature we saw was kind of changing over time, kind of a little bit of a period. So I actually have two different plots here, I think. Let's see here. So, okay, so this one right here is showing a difference. Oh, this is the original data right here, I think. Let's just go ahead and plot this out so I can see it. There we go. So this is the original data right here. And this guy right here is our differencing. So you can see here is that we don't have any differencing here. We can see there's a periodicity in here. And since I know it's temperature, I'm going to use periods of 365. So 365 days, we expect the temperature to kind of cycle through. And we can see is that basically we get rid of that seasonality, this periodicity, right? Kind of going away, which kind of makes sense, right? We basically can just say, hey, what's the difference between this year and last year's value? And just see how this goes through. And you can still see there's a little bit of fluctuation, but for the most part, it's much different. We got rid of all that seasonality, so we can explain it. Okay. Does that make sense to everyone? Cool. And one thing I, again, want to emphasize is just like how simple this was. Like, think this is the original time series with no transformation, doing a difference, and we basically have a stationary thing compared to trying to do a transformation and then trying to find the rolling mean. And then you can imagine like finding the right proper rolling mean too, like maybe only 5 days. Do we do exponential weighted mean? Like, in reality, it's that usually your naive model of just differencing from the previous value it usually does a pretty good job. So just kind of that strategy exists. So we saw kind of how to manually pull out these different parts. This is where our decomposition kind of happens. So we were kind of removing trends, which again, the reason why we're removing trends is just so we can basically say we can explain it, right? And our decomposition allows us to say, okay, let's go ahead and pull out all the different parts of the trend. How much of it is seasonality? So how much does it basically have a periodicity? How much of it is it like a linear, or exponential upward or downward trend? And then the rest of it, hopefully, is just noise, random, irregular, remainder, however you want to phrase this. I keep saying noise, and I want to make this clear because I think I've said this before to other people, and I think it wasn't super clear what I was trying to say. Is when I say noise, it doesn't mean that it's like just random. It means that there's other features likely contributing to this extra fluctuation that's not dependent on time. So just kind of know that it could be random noise, but a lot of times too, we can say that noise is basically all the extra details. If you think like the stock market, if someone puts out, like if a company puts out a specific tweet, that will change the price. And that's not explained with just looking at the time itself. There's other factors that are coming in to explain that kind of fluctuation in the time series. Okay. So I also added this part right here, which I believe is mentioned in the curriculum, this additive and multiplicative, I can never say this word properly, multiplicative part. And one thing to kind of note is that we can have something where we have our, kind of like increasing over higher and higher and higher. And you can see the average increasing up and up and up. And we can see something similar here where the average is also increasing higher and higher and higher. However, these are two different kind of series going forward. Is that this one basically, the average is kind of moving up, but the fluctuations, right, doesn't change. Basically, like the height of this fluctuation does not change, the amplitude, if you're familiar with like wave mechanics and stuff. But this amplitude of this fluctuation really stays about the same, like this blue envelope, where a multiplicative basically has more people like come in and then drop down. So you have larger and larger swings. And so you actually will see this kind of going up and up and up. And so this is kind of an important way you can think of things. Like I think we'll see one in this example in a second, where you might think of something like number of people boarding a plane, like number of people who fly. Over time, more and more people will fly. But that might also mean that there might be higher swings where there's a lot of people flying in the holidays and then less people, less people in the off season, stuff like that flying. And so you might actually see, instead of more of an additive seasonality, where basically the same pattern is going up and up and up, is instead you might have a much more like larger swings, even though this average is going up continuously. Okay, does that make sense to people? Like the difference between these two ones? Cool. See nods and thumbs up. Awesome. All right, so good. Passengers.csv. So I believe this is, if I remember this right, I believe this time series is based around like number of people flying or traveling or something like that. I want to say it's like airplane flying. This is from the curriculum, if anyone recalls what this data was exactly. I probably should have written it down. But you can see here is that our time series is increasing up and up and up. And you can see right here, there definitely is this increase in, what's it called, in this amplitude. And so was this additive or multiplicative?
Multiplicative.
Right. So basically these fluctuations are getting larger and larger and larger. And what's really nice, you can probably see they're very similar. Like if I see each of these peaks, they're very similar to each other. So there definitely is some seasonality within here, right? It's pretty strongly shown. So let's do a log transformation to kind of flatten this out to make it a little bit easier for us to see like it going upwards. So let's see here if I do this guy. There we go. You can see here it's a little more flattened out, right? More linear. So there is a little bit exponential, which is a little hard to tell. But I think you could probably see a little bit there might be exponential. And remember, exponential trends tend to look linear at the very beginning. So it's useful for us to do like a log transformation here. So you can see it's a little more linear here. And we can see we also get rid of that heteroscedasticity where we're basically getting higher and higher and higher. So now these things look about equal to each other, right? So now we get much more like an additive trend. So let's do this next part. So now what we can do is actually this part from stats models. So stats models has a lot of extra tools for time series itself. And we can actually use a seasonal decomposition to do the transformation of that time series. So this guy and say, hey, decompose it into its trend, its seasonal, and its residual. So really nice now that we can just pull this out, but versus trying to like pull it out individually. So we run this guy, and just to see the different plots, we can see now our different trends. So here's our log transformation right here. We can see the upward trend kind of pulled this out, basically found the best trend right here. We can see the seasonality, so we can see like what that looks like, which you can kind of see that going on here. And then this right here on the very bottom is the gold. Like this is kind of like ooh, this is the interesting stuff. So this is all the residuals. And like I said, like kind of a quote unquote random noise, but this is more like the stuff that we can't explain directly with just time itself. So you can kind of see here just some little fluctuations, and you can see the scale going on here. But what's really interesting, I think, is from between here and here, from 1954 and 1958. And there definitely seems like a lot less like fluctuation going on here. Seems pretty consistent. In fact, it seems pretty like zero. And so this could be caused by a lot of things. With one group, I think this was about, if anyone remembers, I think it was like airplane passengers. Okay.
Yeah, I think it's all about planes. Yeah.
Okay, yeah. So this might, for example, anyone got ideas like why this might have kind of calmed down in the middle of 1954 and 1958? Yeah, it might be kind of weird. One suggestion I've heard is like maybe something to do with the Cold War. It's like maybe less people were traveling around for certain things, maybe certain bands and stuff like that. I think someone had mentioned, I'm not a history buff, but something with like maybe like the Cuban, like people, I think there was a Cuban embargo about this time, I think if I remember this right. And it's like maybe, for example, the people who were traveling a lot less now because all of a sudden there's a Cuban ban, and then later on, people found other places for them to travel. So you imagine you plan for something like a year in advance, and you're like, oh, I can't go there anymore. So less people travel. So that's a possibility. There could be a whole bunch of other reasons, or to be quite honest, it could be just completely random. This could just be a pure chance. But this is the story stuff right here. So this is kind of like the nice stuff that you want to try to dig a little deeper. Okay, cool. Does anyone have any questions about like how this is useful together between like looking at the original and then breaking down the trend, seasonality, and residuals? Okay, any questions so far? Sound like pretty good review right now? Okay, cool. So kind of going through a little last part, we're going to look at the residuals, right? And we want to see, hey, are these residuals stationary, right? Basically, can we start just going from here? So if it isn't stationary, it means there's extra time information in there, or if there's other stuff we can use time to help explain parts of these residuals. So let's go ahead and just do this decomposition. We're just, not decomposition, we're doing the drop null values over here. And let's see here, we're using our dickey-fueller tests. So from add Fuller. And like we said before, let's here. In this case, what am I doing? My rolling statistics here. Just want to make sure I know what I'm doing here. Okay, so I'm just smoothing this out a little bit more for us to kind of see a little bit better to see, because like we don't need to care about the next fluctuations, really care about like, is this overall changing over time? And when I do this dickey-fueller now, we should hopefully see that our p-value, good, our p-value is very low, which means that it is stationary, right? So this guy right here says, okay, we have a stationary trend. We're just like, cool, awesome. And I'm looking at this now. I want to make sure I have this right. Why did I even do this? I gotta be honest, I don't think this is supposed to be here. Pass Victor, you did it again. Okay. You don't see how this, does anyone see how this pulls into here? I don't think this has absolutely nothing to do with anything. Yeah, there we go. That's beautiful now. All right, so you can see here the DF tests. That was the only real reason why we use this. Or is your DF test, DS? Yeah, okay, cool. That makes me feel better. I was just like, I don't know what I'm doing the rolling means. All right, so any questions overall, like how the trends basically can be pulled out, or, you know, kind of the overall process of like going with this? No, pretty good. Yeah. Oh, sorry, Phyllis. It's hard to hear you.
I mean, I have a question about the residuals. There are kurtosis, but when you just plot it, there's a kind of huge outline in some part of residue. Is there a way that we can do, or we just leave it alone?
I'm sorry, Phyllis. I really can't hear you. Can you like move closer to your mic, or it sounds like you're kind of far away.
Okay, well.
Oh, much better.
Okay.
Oh.
Okay, for residuals, is it, if there is a kurtosis in the residuals KDE plot, is there anything we can do about it?
So you're talking about more the distribution of the, like if you take the residuals
yes.
and see the distribution of it?
Yes.
Not exact. I mean, you could do a transformation on the residuals to see if you can do more on there, but the main thing is to say, like, what do you need? Like, the main part is like, you know, what do you need to do with your residuals? Like, if you're trying to do.
Well, actually, my concern is like having that kind of residual, would that indicate that the model is not functioning well, or is that just not a problem?
No, I think ideally, like a perfect model would have low kurtosis, right? So we would have something that's more normally distributed. We have essentially random noise on this, right? It probably technically suggests that there would be maybe a better model. In reality, is that there might not be a better model, or like you might not be able to find a model that can do a better explanation without more information. So that's where the judgment call of saying, like, you know, how high of kurtosis is it? Is it like really skinny? It's like, is this acceptable? Or is it, it's got some kurtosis, but we can still proceed in basically doing more statistical tests on it, or saying, yes, this model is good enough, at least for our needs.
So, okay, so we can just leave it alone if it's not too significant, I mean.
Yeah, and this is where like you'll never get a perfect normal distribution in any data that you ever get, because life isn't perfect, right? There's always a little bit of extra, like, you know, chance and randomness that you might not have a perfectly normal distribution, even if it's supposed to be. And that's where the kurtosis is like, really, it's like if you have extreme kurtosis and you're like, this does not look like this residual, essentially, it's not, you know, white noise, this is not a stationary model, it's not normally distributed, then it's like, okay, we need to get a better model. But if it's like slightly off, I think you, for the most part, you can say, okay, we can go from here.
All right, got it, thank you.
No problem, cool. So good kind of segue and then to our next part, which is going to be the actual modeling aspect.